Hello and welcome to this talk about learning and forgetting in Spekkens toy theory. I'm Ladina and I'm about to start my PhD at ETH Zurich, and this work was part of my master's. So what was the motivation for this work? It is we would like to model ourselves as physical agents that can reason and make predictions about in a world that is governed by some theory. And we want these agents to have a physical memory, which is also governed by that theory. And we want them to be able to apply epistemic logic. So if an agent knows that A implies B, and A holds, then the agents can follow that B also holds. It has been shown that in quantum mechanics and box world, such agents can come to contradictions. And in this work, we're going to look at these agents in Spekkens toy theory, which is an epistemically restricted theory. So why are we using Spekkens toy theory? So we want to explore alternative theories to quantum mechanics to see what makes quantum mechanics so special. And this theory reproduces many phenomena of quantum mechanics, but it is not equivalent to quantum mechanics. In particular, it is non-contextual and a local hidden variable theory. So the outline for this talk, first we're going to give a quick introduction to Spekkens toy theory, then we're going to look at memories and predictions, at mixtures and forgetting, and then at the lack of multi-agent paradoxes, and then we're going to look quickly at the generalizations of Spekkens toy theory. So let's start with Spekkens toy theory, which distinguishes between two kinds of states, so ontic and epistemic states. The ontic state is the state of reality. So here the system would be in state 1, if there are 4 states, 1, 2, 3, and 4. And the epistemic state is then the state of knowledge, which is what we know about where the state is. And here one could know that the state is in 1 or 2. And as I mentioned, Spekkens toy theory is an epistricted theory, which means there's a restriction on the knowledge we can have about the state. And this is the knowledge balance principle. And it's kind of modeled after Heisenberg's uncertainty principle. And it says if one has maximal knowledge, then for every time, for every system, the amount of knowledge one possesses about the ontic state is equal to the amount of knowledge one lacks. So one can see this kind of as a scale where the unknown and the known balance each other out. And the known is then the epistemic state, and the known and the unknown together form the ontic state. Let's continue on about having this kind of quantifying it, because we can only say we have equal if we know how much we have. And this is quantified by yes-no questions in a canonical set. So let's start with explaining what yes-no questions are. That's very intuitive. We just ask a question which has yes, no as an answer. And one of them, for example, is the ontic state in 3 or 4. And this has either yes or no, which are indicated by the yellow, by the green and the red. And a canonical set of questions is the minimal set of questions, yes, no questions, such that for each ontic state, there's a set of answers which characterizes this ontic state uniquely. So here we just need 2 questions. So the states that are permitted by this are all of these states. So these are the states where one has maximal knowledge. So the knowledge and the not knowledge balance each other out. And the last one is a state we don't need to have maximal knowledge, where we just know nothing. We don't know where the ontic state is. So we can also kind of find an equivalence to some qubit states with these states. To see this a bit more, to see some examples of this correspondence, if we look at the states that correspond to 0 and 1, these states have 0 overlap, so the knowledge does not overlap each other, just as the quantum equivalents do not have states overlap. Then if one looks at 0 and plus, the states have half overlap. So we see 1 state where if we know it, it could be, but not in the others, which is similar to having these states having half overlap in quantum mechanics. Furthermore, we can also arrange these kind of on a Bloch sphere, but it's no longer a sphere because we don't have this continuous space of states. So let's continue on with measurements. Measurements are partitions of all ontic states into valid epistemic states. So for example, if we do a measurement where we have two outcomes, the red and the green, on the state, and the result is green, then we can conclude that the state before the measurement must have been 2, because that's the only way we could have gotten green. So is this a violation of the knowledge balance principle? No, because we knew before the measurement this must have been the ontic state, but the measurement can perturb the state. So we just need to make the measurement update such that the state after the measurement doesn't violate the knowledge balance principle. So how do we do this? Let's say, again, the same measurement on the same state, and we want the measurement update to be such that it's a valid epistemic state afterward, and we have repeated measurements yield the same result, just as in quantum mechanics, where if we perform a measurement, we disturb the state, but this disturbance is such that if I measure again and again the same measurement, I will get the same result. So the right measurement update that does this is then to randomly apply a permutation that permutes the ontic state from 2 to 3 or from 3 to 2 if it was there, or otherwise it just leaves it, or it does nothing at all. So on this state we just considered, this would mean that if the ontic, we know that the ontic state was this one, so the permutation is randomly applied or not. So after the measurement, we don't anymore know if the ontic state was 2 or 3 because it was permuted with probability 1/2, or it was not permuted with probability 1/2. Let's look at transformations. So transformations have to be such that they map a valid epistemic state again to a valid epistemic state. So for example, we could take the state, a transformation which has many to 1. This would not be a valid transformation because we can always engineer such a epistemic state that it maps this to 1 less. So we have more knowledge, which would then violate the knowledge balance principle. We can also have many to 1 transformations, which then can also be made such that they give us too little knowledge, such that it also doesn't fulfill the knowledge balance principle. Or one can have 1-to-1 transformations, which are just in the end permutations of ontic states. Here one has to do these transformations, one has to add a little asterisk that one can do these transformations in the case that one obtains them in the Stein-Spring dilation scenario, where one takes a second system, does a permutation on the entire system, and then traces out in a toy sense the larger system, the other system. And then one also can obtain a many-to-1 transformation, but this will yield in a correct transformation. But general many-to-1 transformation, one-to-many transformations are not allowed. So let's look at this composition of systems. So composed systems we display by a grid, by this 4x4 grid, where each point corresponds to an ontic state on each of the system as indicated by these numbers. Then we can form product states. So if we know that both Alice and Bob are in these states, we can then yield this as this product state, which can also be seen as the state 0, 0, as the analogon in quantum mechanics. But the composed states don't need to be product. One can also have correlated states. where here we know less about it, so it can be seen similar to a mixture in quantum mechanics, because this state would be the analogon of the 0, 0 state, and this state would be the analogon of the 1, 1 state. So this can be seen as the analogon of the 0, 0 plus 1, 1. 0, the mixture of 0, 0 and 1, 1. So there is one more condition we need to add to the knowledge balance principle if we consider multiple system, and that is that the knowledge balance principle has to hold for each of the subsystems. So if we take, for example, the state, it would fulfill the knowledge balance principle globally. But if we look at the knowledge Alice has about her system, this is a state that does not fulfill the knowledge balance principle. But what Bob knows about the system would be okay. So this would not be a valid state because of that. But this kind of rule also leads to an inductive system of checking states. So if I have a very large system, I need to consider all sets of subsystems to make sure that my state is actually correct. So let's look at transformations in composed systems. Transformations have to map valid epistemic states to valid epistemic states as before. But we can no longer only use all permutations, but we have to restrict ourselves to certain permutations, because if we look at this transformation, which is certainly a permutation, and let it act on the state, which is also a valid state, the end state will be a not valid state, and this is not an allowed transformation then. But one transformation that is allowed is the toy C0 gate, which is kind of the toy analogon to the quantum C0 gate. And to kind of show some examples, we just first look at the 0, 0, or the analogon of the 0, 0 state, which is then going to the analogon of the 0, 0 state under this transformation. If we look at the 0, 1, 0 state, it goes to the analogon of the 1, 1 state. And if we look at what happens to the analogon of the plus 0 state, it goes to the analogon of this kind of Bell state. And the state is very similar to this, because we also have this kind of correlation, because now we no longer know what the state is, as here we don't know if one system is in 0 or 1, but we do know that if we do measurements on this, the outcomes will be perfectly correlated. So now let's discuss a bit more about what the relations to quantum mechanics is. And there are many phenomena that can be reproduced in Spekkens toy theory. For example, non-commutativity of measurements, coherent superposition, no cloning, interference, teleportation, dense coding, entanglement, monogamy of entanglement, and many more. So now let's talk about memories in quantum mechanics. So let's consider a situation where we have Alice, which has her memory and does a Z measurement on her system, which is in a plus state, and her memory is initially in the 0 state. Then she does a measurement and she gets either 1 or 0 as a result. And if she gets 1 as a result, she will change her memory to 1. And if she gets 0 as a result, she will leave her memory as is. So how does Bob model this, who observes Alice measuring this? So for him, the measurement of what changes in those two systems is just a C0 gate. Because in the end, after the measurement, the two will be perfectly correlated. So if Alice have gotten a 0, then her memory will be in 0. And if she's gotten a 1, then her memory will be in 1. And we can do a very similar thing in Spekkens toy theory. So again, consider the same situation where we have Alice in her lab and Bob observing Alice. And Alice does the toy analogon of a Z measurement. And she measures her system, which is in the toy analogon of a plus state, and the same her memory is in the toy analog of the 0 state, and if she measures 0, then she will, or green, she will leave her memory, and if she measures red, she will change her memory to the toy analog of the 1 state. So the blue will swap to the other side. As Bob, as an outsider, just sees this again as her applying a C0 gate onto Alice and her memory. Now let's talk about predictions with certainty in Spekkens toy theory and also quantum mechanics. So let's first start with quantum mechanics, where we have Bob and Alice who share together this Bell state, and they want to measure, or Bob measures the Z, Pauli Z, and on his part of the Bell state. And he knows if he gets result +1, then the end state will be 0, 0, 0, and if he gets -1, the end state will be 1, 1. So he can make these predictions if he gets +1, and Alice also measures Z, then she will also have to get +1. And similarly, if Bob will get -1, then Alice will also have to get -1. So in this way, Bob can make from his measurement predictions what Alice will measure. And a similar thing can also be done in the toy theory, where we have a measurement which is now yellow or green. And if the result is yellow, the shared state, which is this analogon to the Bell state between Alice and Bob, will update to this state. And if it's red, it will update to this state. And Bob can then reason that, or know that if he measures yellow and Alice measures again the yellow-red measurement, she will also get yellow. And the same way, if he gets red, Alice also must get red. So now let's talk about mixing and forgetting. So in quantum mechanics, if we have some +0 dispenser, which then dispenses one of these states and shows which state has been dispensed, and Bob leaves it on his desk and then forgets about it, then he doesn't know what has been dispensed before. So the only thing his state of knowledge is then the equal mixture of the two states. And in toy theory, this would also be described by the mixture, where if we have a similar situation, we have a dispenser which dispenses one of these two states, but the mixture of these states is now not a valid state. So there are certain two states, in this case, these two, for example, where if one forgets it, which one it is, we cannot actually, the resulting state is not a valid state. Which means that in the toy theory, Bob cannot forget which state he had. So now let's go and talk about the multi-agent paradoxes. And the agent setting that was considered to get multi-agent paradoxes in box world and quantum mechanics was this kind of setup. So we have Alice, which looks at the system R, and Bob, which looks at the system S, and both Ursula and Wigner, which observe Bob and his system S, and Alice and her system R. And when these agents do reasoning each other in quantum mechanics, they can reach contradictory conclusions. And in Spekkens toy theory, one can show that these reasonings that lead to contradictions in quantum mechanics do not lead to a contradiction in Spekkens toy theory. So what is the intuition behind this? And it is that the toy theory is non-contextual, so measurements just reveal what's already there. And this revealing what's already there is, or what's already there is not contradicting, so the contradiction cannot occur. So what did we assume in the proof of this? It is that agents reason as in the previous setting. They use the toy theory, and as the memory update, they use the toy C0 gate, and that they can actually reason about each other. And we can generalize this proof to having settings with n Alice's and m Bob's, and it's also easily extendable to considering a different epistemic restriction in some settings. So now what can we conclude? In this work, we introduced a memory update in Spekkens toy theory. We formalized what it means to have predictions and conclusions with certainty. We proved that the Frauchiger-Renner-like paradox does not exist. And in future work, we would like to consider mixtures and different epistemic restrictions, where maybe this weird property where certain states cannot be forgotten does not occur. Paradoxes, or the same paradox for different epistemic restrictions and kind of different settings of agents. In further results of this work, we also review the 3 different kind of formalism of the toy theory. That is the epistemic picture, which I described in this talk, but also there's a stabilizer formalism and a generalization of the toy theory to arbitrary dimensions. So we would not consider qubits, but qubits or continuous dimensions. And in this work, in this paper, we also generalized the notions of entanglement, allowed measurements and superpositions as they were introduced in the epistemic picture or in the stabilizer formalism to arbitrary dimensions.